Okay, in the interest of being on time, because we have some people watching this thing online, we're going to get started, and the morning session today is going to be talking about somewhat more applied problems than what we've seen so far. Our first speaker is Uros, and he's going to be talking about partial Hessian inversion in really large dimensions.
Yeah, thank you. So I didn't know what kind of title to give, so I gave a title which sounded more provocative, but it really, what we're trying to achieve is we're trying to do marginalization, and I'll explain that that's the same thing as doing, in matrix inversion, Hessian matrix inversion, but only for a few variables, okay? So I'd like to thank the organizers for inviting me, and I was not sure what to expect from this, so if I can explain to you what the problem is, and if I can get some feedback, that would be great. Okay, so as I said, I wasn't quite sure what the connection is between the problems we are solving and the problems of this conference, but we are also trying to do stochastic linear algebra problems, so there is some connection there. So let me start by talking about the problem itself. I'll define a more specific problem in the context of least square on the next slide, but let me first start telling you about what we try to do when we try to do data analysis. We have a lot of latent variables, so these are the variables that create an event or events that we'd like to analyze. In our context, I'm a cosmologist, so I try to do study the universe. I observe the galaxies. But the galaxies are not, the galaxy positions, for example, are not necessarily something we care about. We care about more about the hyperparameters that created that distribution. Okay, so there's a whole bunch of latent variables that are, for which we know their prior distribution. In fact, it's a multivariate Gaussian. And, but what we would like to learn is what those observations, like galaxy positions, tell us about the underlying properties of the universe. All right, I'll explain more what I mean by this. So we care about the hyperparameters. We care about what determines these latent variables, not the latent variables themselves. So that means in a typical statistical inference problem, you would marginalize over these latent variables. The first question is, do we really need to marginalize? Can we just maximize, do maximum likelihood estimation of all the variables at once and just go away with that? The answer is yes, we need to marginalize. You can get really wrong answers if you just try to marginalize latent variables and their hyperparameters at once. Okay, I won't go into this, but it's well known that maximum likelihood estimator is biased, even in asymptotic limit, if you have same number of variables of observations. There's a famous Neyman-Scott problem, for example. And so this is the same statement here. Basically, you can get biased results if you don't do marginalization. Okay, so how does this relate to the linear algebra? Well, in linear algebra, for example, imagine that we had a full rank Hessian for all of these variables. Both the variables, yes?
What is the Hessian of?
Yes, I was just going to say. Imagine that we have the Hessian of all of these variables, both the latent variables and the parameters that we're trying to estimate. So this would be second derivative information against the latent variables and against the parameters.
What function is it the Hessian of?
Let me get to that on 2 slides. It's going to be least square. Yeah. So for now, let's just assume that we have a Hessian. Then, if we want to marginalize over these latent variables, what we would do, we would invert the Hessian. We'd take the rows and columns that correspond to this, to the parameters we care about, and we would get rid of everything else, right? And then, if necessary, we invert it again to get the precision matrix out of the covariance matrix. All right, so that's the procedure in low dimensions. The problem is that in high dimensions, this doesn't work. This process scales as n cubed. As soon as n is more than, I don't know, 100,000 maybe these days, this is not possible anymore to do. Okay, so let me just, this is trivial. I assume you've all seen this, but let me just, go through this again. If we have to do marginalization in 2D, imagine you have a 2D Hessian. This would be these coefficients here. I wrote them as an inverse of the covariance matrix because that's what Hessian is. All right, but these are, think of this as being coefficients. You want to marginalize over one of the variable to get the posterior just for the second variable. Then what, if you do this completion of squares, you add, probably you've seen all this before, but anyway, you add something, you complete the square, you do then the integral over a in this case, and you're left with something which is inverse of this 2x2 matrix, and then you just take the element that corresponds to the variable that you care about. Okay, in this case, it would be b variable. Okay, so this is the inversion, right, of the matrix. Okay, so let's move on. What is that we are? How do we get the Hessian? What is our problem? We're trying to solve the regularized least square problem. You have some data. Okay, in our case, let's say galaxy positions in the sky. We have some model to predict this data. This model depends on a bunch of latent variables, which we call little s. All right? The data are noisy, so there's some noise matrix in principle, although we can assume that the noise matrix is diagonal and just a multiplier times the identity in the simplest case. And we can assume, for the simplicity, that noise is Gaussian. Right? So then we can write down the probability distribution of the noise just as a multivariate Gaussian, which is just data minus the model. As I said, I've introduced these latent variables here, S, and we often know their prior. In fact, in the context of the studies that we care about, the prior is really what we care about. We don't care about the latent variables themselves. We care about what their power is. So we care about their power spectrum. All right. So that means these latent variables are distributed as a multivariate Gaussian, and it's best if one can find a prior where this expression is diagonal, where this matrix here is S is diagonal. In our case, for example, this matrix S is diagonal in Fourier space. Okay? So now what we have is that the joint probability distribution is the product of the two. And the problem is that we have we have two matrices. One is diagonal in one space, in configuration space or real space. And the other one is diagonal in Fourier space. So when you put the two together, you get basically a non-sparse full rank matrix that is non-sparse in any basis. That's not sparse in any basis. Okay? So you cannot easily do the matrix inversion. So for example, if I linearize this problem, if I say f of s is just some matrix times s, then the covariance matrix of the data one can show is just given by this expression. In this expression, you see we have to be able to compute the determinant of the covariance matrix and the inverse of the covariance matrix. Covariance matrix is this thing here, and as I said, it's full rank and typically cannot be diagonalized in any simple basis. So we don't know how to do matrix inversion or the determinant if the dimensionality of the data is very large.
Just to understand this expression in the exponential better, this is x c inverse
this one?
x.
Or this one?
There, yeah.
Yeah.
In my language, this will be x transpose. This is a number, right?
Yeah. There's transpose.
So you really don't need the inverse. You just need to be able to compute the exponential fast.
Yes.
With inner products.
You need to be able to apply C inverse to a vector fast.
Right. That's what you need.
Yeah. No, it's in fact, it usually, don't worry so much about this term. This term actually turns out that we don't need to know that much, but this is the hard term. The determinant is the harder term.
Estimating the determinant efficient.
Yeah. Yes.
And the size of the matrix that's the number with the data or the
number of data. In this context, the number of data. Then I'll translate it later into number of latent variables. Both the data and latent variables can be in millions. In fact, the latent variables that we plan to work with is 10 to the 10. That's why I had this 10 to the 10 in my example.
And so you are trying to optimize the latent variables?
I don't care about latent variables. I care about the hyperparameters. In this case, their power spectrum, for example, this S. This is power spectrum because I said this is diagonal in Fourier basis.
That's what you want to find?
Yes.
And how many hyperparameters do you have?
Sorry?
How many hyperparameters do you have?
How many?
Yeah, hyperparameters. do you have?
Oh, well, this is a continuous function. Yeah, I mean, in this example I'll show I'll have 30 or 40 or something like that. So.
What's S and C then?
Sorry?
What in C? What is S?
S.
Is it a diagonal matrix?
Yes. In Fourier space is diagonal matrix, yes.
Positive, definite, and diagonal.
Sorry?
Positive, definite.
Yes. Yes, it's a power spectrum, yeah.
So do you know anything about the structure of C? Is it strongly diagonally dominant so that you could get a good approximation to the
No, that's because the data, as soon as you go into impartial data, you have gaps and holes, you have finite survey, then C is not diagonal dominant. It's really full rank, you don't know much about it. I mean, you know something about it, I guess. If you had perfect data, yes, it would be diagonal in Fourier basis.
No, not diagonal, diagonally dominant. Are the diagonal elements large so you can get a good approximation?
Diagonal dominant in configuration space, in real space, it definitely is not diagonal dominant because there are correlations between the data points on all scales. Basically, this point on the sky is correlated with that point on the sky. You know, that's what inflationary theory does for you. Everything is correlated in our universe. That's great because there's a lot of information there, but it makes the problem much harder. The condition number of the matrix is also horrible. Often, it's very large. Okay, so let's move on. So here I have linearized this thing just for you to get some intuition. But the problem we are working on is actually we are trying to do this nonlinear evolution actually. So this f of s, you can think of it as a full nonlinear evolution of the universe from its initial conditions, which are these Gaussian latent variable fluctuations, all the way to a very nonlinear picture of galaxies in the sky. Okay, I'll show an example later. But the point is, this is a fully nonlinear evolution. We ran partial differential equations with n-body simulations. As I said, we often work with 10 to the 10 latent variables, 10 to the 10 particles, we say. It's an n-body simulation, and this is extremely expensive to compute. All right, so the point I'm trying to make is we're dealing with a situation where likelihood evaluation for each configuration of latent variables is extremely expensive to evaluate. You're talking about tens of hours for a single evaluation. And we want to, I don't know, sample or get some kind of solution which corresponds to the actual data in the sky. All right? That's the difficulty. Okay, we'll assume that we have gradients, access to the gradients of f with respect to all variables and parameters. This is an PDE system, so we have developed backpropagation algorithms to get the gradients with respect to everything. So everything means all those 10 to the 10 parameters. Okay, here are my collaborators on this. So the first question is, can we do this brute force by just sampling with MCMC? Now, if you try to sample with the Metropolis algorithm, which doesn't even have gradient access, then it's kind of hopeless. You have curse of dimensionality. It just has no way to find where to go to find these 10 to the 10 solutions and to sample them properly. You can do better if you try with Hamiltonian Monte Carlo, where the gradient is available. But still, even in this case, people who have tried this find that it takes thousands of likelihood evaluations to get a single independent sample. Okay, because the samples are very correlated in the context of HMC. So, moreover, MCMC in high noise regime converges very slowly on hyperparameters. That's just due to the fact that, MCMC is sampling from some kind of through posterior, and it's kind of hard to tell for the sampler what's real and what's fake, because it has to put in fake stuff to make up for what we don't know about. Okay. We don't think we can do this with MCMC. What about optimization with gradients? Let's try that. So this is what I will be talking about. There's a caveat, of course, since this is nonlinear evolution. We are talking about non-convex optimization. So there's no guarantee that whatever we find is the global minimum. But nevertheless, I'll show, we get actually very good results, so we think we are probably close to the global minimum.
Do you care about finding the local minimum, or are you happy like with the stationary point, which could be a saddle?
Well, I mean, the correct thing to do would be to find all of the minima and then average them with a proper importance sampling weights. Okay, the approximation we're making here is that we're descending as far as we can, and we declare that to be the deepest minimum, so that we ignore everything else. Right? That's the approximation we're making here. If you work in these kind of very high dimensions, there's really not much you can do. There's no way to, there's just no way to find that if there's another minimum which is deeper, especially if you have to go across the hill to get there.
No, but you can get stuck at the stationary point.
Yeah, well.
And there are methods that actually try
Sorry?
to avoid those. There are methods that.
Yeah, right. And of course, we try to use those methods. Yeah. We try stochastic stuff. We try, I should say this is least square problem. So in least square problems, usually you don't actually get stuck on saddle points.
Sure. Yeah.
Okay, so let's first ask ourselves, how do we find the best latent variables? All right, so we try to, you follow the gradient. Let's take a log of that posterior that I wrote down there. It's essentially just a regularized chi-square now. You have the data, and then you have the prior here, the L2 regularizer. And you take a gradient of this stuff, and if you take a second derivative, then you also have the Hessian. We never evaluate this, as I said, because this would be a 10 to the 10 square matrix. But in principle, at least there's a conceptual Hessian matrix there. And you see now I've converted this Hessian from data to the latent variables. So it's actually inverse of this and inverse of this. If we work with 10 to the 10 latent variables, then we're talking about this matrix would be 10 to the 10 square. Okay, so we don't actually use Newton's method. We use quasi-Newton's methods, or we do use a Steinhauer conjugate gradient method, which is actually second order, because we have developed also the dot product between the Gauss-Newton version of the Hessian times the gradient. Okay, so that's how we approach this. We're descending slowly in these very high dimensions until we find something. All right, until we hit the minimum, and we declare that to be our global minimum, and we then try to ask, now that we are here, what do we do with it? How do we get the hyperparameters? Okay, so as I mentioned before, we do have access to the analytic gradients of both the latent variables and the hyperparameters. So let's call these hyperparameters, Z or something like that. So what we want is basically get the gradient and the Hessian of these hyperparameters marginalized over all the latent variables, which we call S. All right, so again, as I mentioned before, one solution would be with the linear algebra. We would have to therefore invert this very large matrix, and that's just not possible. So what can we do? What's the advantage here compared to the general problem is that we do have actually the generative model to create these samples here. So whenever we have basically a probabilistic graphical model, so we can model from the latent variables all the way to the data, then we can do this. Now, does this help? And the answer is it does help because, and let's look at this in the context of sampling. Let's try to replace now this marginalization with a statement, well, we can just take sampling averages. What do we mean by this? Let's take a gradient of this marginalized log posterior. Okay, what is marginalized log posterior? We take a gradient with respect to the integral over these latent variables. Now I can propagate this integral, so I can write this probability. You remember I had this loss function on the previous slide. That's just minus log probability. So I can rewrite this as this integral of ds e to the minus L. And if I plug the gradient on this, then you see I can get a gradient on the loss function. But it's really averaged over the full probability distribution of the latent variables. So you can think of this as the gradient averaged over all the samples of the latent variables. You can do something similar with the Hessian. Now you have to take second derivative. You take another derivative of this. And let me just show you the final result. The first part of the answer is expected. You just get a second derivative of the loss function sampled over all the latent variables. So think of this as the partial derivative part. If this were, if the hyperparameters were not correlated with the latent variables, this would be all we need. But unfortunately, they are correlated. And so now we get a term where you see it comes with a minus sign. And there's a term which actually takes the gradient, and you square the gradient, literally, and then you take the average of this.
So it's like a variance then.
Sorry?
Is that like a variance then, the second term?
Yeah, actually, let's look at what this looks like in the context of a just 2x2 matrix. Again, the same context I've shown you before. We can take the gradient in respect to the first variable. It's and think of it if you have a 2x2 matrix. You have this this Hessian that I had before, sigma inverse 1, 1, sigma inverse 1, 2. So this is the gradient, the second derivative. But now we need to average this over this term over z2, for example. And if we do this, then this term here actually gives us this. And the bottom line is when we evaluate this expression here, we get exactly what we want, which is the inverse of the matrix, of the Hessian matrix, and then component for that element that we care about. All right? So this procedure here, the sampling procedure, gives you the inverse of the marginalized, gives you the row and column of the inverse of the covariance matrix. Inverse of the Hessian, sorry. Right? So it gives you what you want. That's good. And the price you pay is that you have to do these sampling averages. So, well, unfortunately, before I get to how will we do this, so the price we pay is we have to sample now. We have to sample from the posterior. Can we do this? Well, we cannot directly sample from the posterior because, again, even if we had full Hessian, we don't know how to diagonalize or let's do Koleski decomposition to actually be able to draw the samples. It's the same problem as before. If we are in 10 to the 10 dimensions, then we cannot get the Koleski decomposition of the very large matrix. So we cannot directly sample from the Hessian. Now we can, of course, go back and do the MCMC approach and maybe just evaluate a few samples. And I argued before that this is still very expensive. It takes a few thousand steps to get a single independent sample. So maybe this approach works, but it doesn't seem very promising. Alternative is we just make an approximation to the posteriors in the following way. We already had this map solution, the maximum posterior solution of the latent variables. We can run a simulation, draw from, in a simulation we know exactly what we have put in, so we know the true value. We can run the map approximation to this simulation. We get map values for this simulation. And then we add this difference here to our map of the data. The idea is that this will be, we're kind of approximating the posterior distribution of the data by adding this difference between what the simulation would do and what the true answer in simulation is. So basically think about it. If you determine if map determines the parameter well, then this difference will be very small. Okay, if the data are not constraining very well the latent variables, then the latent variables go to 0. And then this difference here essentially, this is 0 and this is 0, and then this is just a sample of the true value. The sample of the true value, so you get correct samples, but of course this sample of true value is useless because it was drawn from a simulation, not from the data, and doesn't actually contain any information about the underlying hyperparameters. Okay, so we've tried this and this works well. We get unbiased results. Now the problem here is that we would also like to have the Hessian, the second matrix, the second derivatives, because we would like to give errors to our parameters that we are estimating. In fact, these parameters are often correlated, so we want the full covariance matrix. Covariance matrix is the inverse of the Hessian matrix. We're talking about low dimensionality here, so it's easy to invert this, so that's not a problem. However, the problem is that this term here, the second term here, this marginalization term is actually very noisy. Okay, so let me show you an example of the variance of if the hyperparameter S is the parameter we care about. So this is our loss function that I wrote. We can take a gradient respect to this. Let's say this S is a function of Z. So just for simplicity, okay. But I'm taking derivatives with respect to S basically. So I get these kind of expressions. Let me not go into all the details, but I just want to point out that this expression here, the gradient, is a sum over all the data points. This term here that I mentioned before, this term that we are subtracting out, is the sum of all the data points times the sum of all data points. So it goes as number of data points squared. So this term is very noisy, all right? And as a consequence, then this Hessian is very noisy. So an alternative is to try analytic marginalization. We try to do the integral over the latent variables first. This pulls out this Hessian again that I mentioned before. I wrote it here in the Gauss-Newton approximation where I dropped the second derivatives. It looks bad. However, when you take a gradient of this expression, you get this kind of expression. You get a gradient of at the map value at the peak of this latent variables, and minus a term which is a gradient of the log determinant of that matrix. Again, this matrix is 10 to the 10 squared matrix. You will have no chance of trying to get this determinant with linear algebra. But what one can do instead, one knows that this gradient, the whole gradient, has to vanish if you run a simulation and you run a simulation with where you know the true value of the hyperparameter, and generate your latent variables with that true value, then you know that on average this gradient has to vanish because the gradient at the correct value on average has to be 0. So that's a way, therefore, to determine this term here. Okay, so again, I mean, to do this, we're running simulations, so we're doing some kind of sampling, but it's a much easier form of sampling. Okay, so and then finally, how do we do the Hessian? We have tried many different things, and we find that the best way to do this is simply with a finite difference.
For noisy matrix.
Well, this matrix now.
So you have a noisy function, then you're doing finite differences.
Good question. Yes, we do take advantage a lot of the sampling noise reduction methods. For example, in the context of this question you just asked, is it noisy? Yes, it is noisy, but if you draw both, let's say for model A and for model Z, ZA and Z, you draw with the same random seeds, then the difference actually is not noisy. Right? So this is one way where you can reduce the noise. And by the way, we do similar things also to get a gradient, right? So, but definitely, this kind of sampling reduction noise methods definitely help a lot. Okay, so let me show you what we're trying to do. We're trying to apply this to cosmology problem. So this is our simulation. We start with very tiny fluctuations, and we move forward into the real data space today. Here's another example. All right, we take fluctuations, tiny fluctuations, like in cosmological background, and then we evolve forward the model, and we get this kind of nice-looking simulations of very nonlinear structures. So this is our forward model. I won't go into details since I'm running out of time, but let me just tell you, we start with Gaussian fluctuations here. These are the dark matter today. You see it's very non-Gaussian. It has voids and filaments and so on. And this is what the light looks like, the galaxy light. So galaxy light only appears where we have the highest density peaks. So this is our generative model, basically. And when we try to reconstruct the latent variables from this is our example. This is the true, it's all done on simulations, but think of this as a truth. Truth initial conditions, truth dark matter, and truth light. And this is how well we reconstructed it. We reconstruct the light very well, the dark matter, final dark matter very well. You see we lose high frequency structure in the initial conditions, and that's because of the structure formation,
so this
basically.
This is an inverse problem,
This is an inverse problem,
where
yeah.
you want to recover the initial conditions.
Yes,
Oh, I see.
yes. Okay, but again, we don't care about this. As I said, we care about the summary statistics, which is in this case the power spectrum of these things. And here is an example. I mean, I'm almost done here. Here's an example where we try to reconstruct this power spectrum. Here I'm showing divide by the truth, just to give an idea how well we're doing. And we also have errors from the Hessian that I'll show on the next slide. But the basic takeaway point here is we are reconstructing something which is around 1 with errors as expected. So we get unbiased results from this procedure, and we would like to argue these are the smallest possible errors one can achieve. Hessian, here's, I think this is the last slide. Basically, here I'm comparing now the diagonal of the Hessian between these two methods that I mentioned. One is a sampling of the modes, and then add these into these bootstrap resamples that I mentioned. And here is an example of how well we do if you have 1 sample, 4 samples, 32 samples. You see there's a lot of noise, especially with 1, and the noise is going down. But the red line is the one that I mentioned later, where we try to do this analytic marginalization. And the point is it's less noisy, and it agrees with the other ones. So we think this is still the best method, that analytic marginalization and then just getting the determinant with the simulation. And in this case, the off-diagonal terms are essentially 0, so we get so the Hessian is essentially diagonal. This is the Hessian of the hyperparameters. Okay, so we have about 4 here down here. Okay, so that's a summary. Doing analytic marginalizations in high dimensions is hard, and standard linear algebra methods definitely fail. Stochastic approaches are more promising, but they are very different in their noise levels. MCMC is probably the worst. We haven't even tried because we think there's no point. But sampling followed by analytic gradients is better. And finally, analytic marginalization of the latent variables followed by sampling is the best. And all of these methods benefit a lot if you try to reduce the sampling noise by using sampling noise reduction methods, like same seed numbers and stuff like that. Okay, and I think that's it. Thanks.
Thank you very much. We can take a couple or 1 or 2 quick questions. If there are none, actually, so a lot of us have actually worked on log debt estimators for matrices that are, they have to be positive definite and they have to have non-zero determinant.
Yes, good. Yeah.
But your matrices are not positive definite.
No, they are. They're covariance matrices, right?
No, but you're adding the random noise that destroys positive definiteness, right?
No, I'm not adding any noise. No. Definitely they are positive definite, and definitely they are.
So there is a lot of work there. I think like 4 or 5 people here at least have estimators based on randomized traced estimation. So this might.
Good. And do they assume low rankness and stuff like that, or?
Do we need any of that?
No, we don't.
We don't need low rank.
It's faster. If the rank is low, but they don't need it.
So that might be a point of
Actually, we have developed ours for inverse problems, and you have an inverse problem, so they're pretty robust.
Yeah.
Thank you very much, Uros. Thank you very much.